Once again, thank you very much for everyone for joining here us today. We are here for the closing ceremony of our project on use of nanobubble technologies in water, wastewater recycling applications. We will be giving a couple of presentations. First, I will be introducing our association, which is the project coordinator. Then I will be presenting the project partners and give a little bit information about our project. And the presentation owners will be giving their speeches one by one. So let me share my screen. Can you see my screen clearly?
Yes.
Okay.
Yes, Simon.
So let me start by giving a little bit information about our association. It's Climate Research Association, and it is established in 2016 in Ankara. It's a non-profit organization, and it's working on various topics such as climate change, its impacts on economy, society, and environment. Our expertise includes climate change mitigation strategies, climate change adaptation, climate risk management, climate finance and policies, and resource efficiency and circular economy. We have conducted a couple of projects. I want to give you some examples. One of them is water sustainability of the Turkish dairy sector, efficiency risks and vulnerabilities. This is a project that is closed. We were the project partner, and it was aiming to establish a dialogue for identifying climate and waterborne risks and assessing the impact on the value chain. It was funded by civil society dialogue between EU and Turkey. Our another project is EU-Turkey Climate Policy Dialogue. We were again a project partner, and this project is also concluded. The project aimed to establish a sustainable dialogue between Turkey and European Union private actors and public institutions in articulation of the climate change policy. So we were developing a climate policy between EU and Turkey, contributing to that. Another project conducted by our association is the Hand in Hand for Resilient Civil Society, improving the institutional capacity of TSOs and strengthening the collaboration with municipalities. We were a project partner, coordinator and implementer, and the project, as the name suggests, was about establishing an effective collaboration between TSOs, public institutions, and private sectors in order to strengthen capacity in various cities in Turkey and thereby increasing the urban resilience. This is a current project. It's on climate resistant and sustainable beekeeping in Marmaris, a case study for pollinator pastures. This is ongoing, and we are aiming to sustain beekeeping activities in Marmaris. We are a project coordinator in this project, and the funding authority is Turkish Coast Environment Fund, Turkey. Another project is on the plastics value chain in Ankara. We are again a project coordinator. This project is funded by GEF Small Grant Program, Turkey, and in this project we are analyzing the plastic value chain at the city scale, and we are trying to provide a circular economy approach, especially for Ankara Metropolitan Municipality, which is beneficiary, and we are trying to increase the institutional capacity of the relevant stakeholders. And finally, this is our current project. The reason we are here today is the investigation of market potential and collaboration opportunities for mainstreaming nanobubble technologies in Turkish water, wastewater recycling industry. This project is funded by the US Embassy Turkey Mission Grant Program. As of this month, the project is closing. We were a project coordinator. Our project partners were the University of Maine and Arizona State University. As I said before, the founding authority was the US Embassy. In this project, we aim to increase the cooperation between US and Turkish scientists and industries in the field of innovative water treatment and recovery, so that we increase the climate resilience of the water stressed regions in Turkey. For this, so how did we came up with this project? If you look at this slide, you can see that according to the Ministry of Environment, Urbanization and Climate Change data, current water, as of 2018, Turkish water per capita values were almost 1,300 meters cubed per person. This data alone showed that Turkey is experiencing water scarcity at this moment, and by the data provided by Turkish Statistics Institute, we are expecting a decrease in this value, but the population will be reaching almost 100 million by 2030 in Turkey. So this was a warning for Turkey that it will be a water scarce and country, and we would be experiencing water stress. Therefore, it was necessary for being more effective, using more effective water treatment and recycling systems in our country. For this reason, efforts were being adopted for green technologies in our country, and our project was the first project that takes initiative in application of nanobubble technology in Turkey, so that we can achieve this more effective water treatment and recycling system used in Turkey. So this was a brief introduction for our project and for our association. So I will be giving floor to other presenters. As a next presentation will be by Ece Akaydemir. She is a board member of our association, and she will be giving a speech on nanobubble technology market and potential application areas in Turkey.
Thank you, Sena. I can share my screen. Do you see?
Yes, we can see your screen.
Okay. As Sena mentioned, I'm Ece Akaydemir from Climate Research Association. First of all, I would like to thank our speakers for joining us today. Sena has already mentioned what is the motivation behind our project and what are the needs and gaps. In this manner, this technology has brought us to this point, and we want the technology transfer from United States to Turkey. And we want to define what are the current problems, where can this technology play an active role, and we have shown it in this project. And I will mention the nanobubble technology market and potential application areas in Turkey in my presentation. First of all, in a technical point of view, if I mention properties of nanobubbles, for a brief information, they have a stable spherical packages of gas in liquid with a diameter less than 1,000 nanometers. They remain suspended in the liquid for an extended period of time due to the lower buoyancy. They have high stability, low humidity, and rapid adhesion onto the hydrophobic surfaces. They have lots of application areas, you know more than me. These are the medicine, disinfection, mining, agriculture, wastewater treatment for the removal of pollutants. And if we look at the application areas or sectors, let's say, if we look more deeper, in the agriculture or horticulture, they improve the water quality, promote root development, foster plant health, lower treatment costs, and in the lakes and ponds, they are more resilient to algae blooms, and they provide healthier lakes, therefore. In the anaerobic digestion, they enhance the rate-limiting steps, increase water mobility, enhance substrate digestibility. And in the aquaculture, they improve fish and ecosystem health, maximize fish growth, and therefore they lower the operating costs. In the oil and gas sector, they can be cost-effective. They might cause cost-effective chemical reduction and water recycling and reduce chemical use. And then the mining, they accelerate the leaching rates and therefore provides the extraction efficiency. In the wastewater treatment sector, they can also be benefited in different states of treatment like aeration, flotation, or disinfection. In the aeration, they can improve oxygen supply efficiency, degradation of pollutants, or in the flotation, they can increase the collision probability and increase the separation efficiency. And lastly, in the disinfection, they approximately 99% faster reduction rate and provides the lower ozone requirements and smaller tank size. Now, when we look at the situation and the examples in the world, we examined lots of examples actually and studies. One of them is for flotation and dissolved air flotation. The problem here is there's a need for the enhancement of performance of dissolved air flotation units in order to provide a cost-effective removal of high levels of soluble biochemical oxygen demand. If when they use the nanobubbles, they provide about 40% of BOD reduction and about 25% increase total suspended fluid removal. In addition to that, the solid content increased from 3 to about 20%. And thanks to the nanobubbles, they save about $50,000 per year. And the payback period is very low, about 3 months, and energy consumption is reduced by about 20,000 kilowatt-hours per year, and energy cost saving is over $2,000 in this example. Another example is winery wastewater. This study is conducted in South Africa. The problem is strong, unbearable odors permeated the community around the site due to the years of dumping, because they discharge their winery wastewater to here, this pond. And they use an Nanbubble device with air intake of 170 liters per minute for this pond with a volume 2,000 meter cubes, and they achieved total daily COD reduction, and energy requirement is reduced. COD removal is higher than the current station, and full odor mitigation is provided in 54 days. Therefore, birds return their natural habitat. Another example is aeration of station ditch. It is the municipal wastewater treatment plant. The problem is the heavy wash down made it impossible to rise the oxygen level, and therefore there is an improper treatment. The benefits are rapid installation, delivering more oxygen than needed, and enabling operators to easily switch between pure oxygen and air. DO is increased from 0.11 ppm to 3 to 6 ppm in the outer ditch, and the sludge amount is reduced as expected. Another example is from an oil and gas sector. The study is conducted for oil separation process. The separation process varies between 80% and 90% effectiveness, and this results in oil loss. They use nanobubbles and increase the oil recovery rate approximately 15%. And they reduce the produced volume water, lower produced water transfer volume, and therefore the cost. They reduce the use of chemicals to treat emulsion, reduce oil transport damage, improve oil and water transport scheduling, reduce site supervision, and they say about $15,000 in 60 days. And the yearly revenue, potential revenue is about $100,000. And lastly, in agriculture sector, we want to show an example. The study area is greenhouse. It recirculates water, including nutrients and dissolved oxygen, to the roots of the plant. The problem is delivering enough oxygen to plants, and they also use nanobubbles. It provides about 300% yield increase and increased yield, 16-month payback period, which is slightly okay. Reduced cultivation time, it's reduced from 10 weeks to 8 weeks, and increased total revenue. And in a final result, they have healthier plants and larger groups. And we examined such examples and studies and merged approximate results in a matrix here. As you can see, in lots of application area, the process efficiency is high. Successful practice examples exist in the world, and their cost savings are high, but payback period is very good, very low. And as I mentioned, in wastewater sector, application areas are divided into 3: process, aeration, flotation, and disinfection. The results are also very good. And now I want to go through with Turkey and its potential, because climate change effects on especially water is felt significantly as in the whole world. Therefore, usage of nanobubbles in wastewater sector might be valuable, so we analyze it deeper. Here you can see the municipal wastewater treatment plants found in Turkey. In 2018, there are about 1,000 wastewater treatment plants, municipal wastewater treatment plants, and most of them discharge to the river. As you can see here, about 50%. Unfortunately, the usage of advanced treatments is not very high, although they show an increase. In 2018, about 48% of the treatment plants use advanced treatment. In 2020, it is slightly higher than the 50%, but this is not enough, actually. We need more advanced treatment to protect nature, to recycle the water in order to combat with the climate change effects. And here you can see the industrial wastewater station, the wastewater status of the organized industrial zones in Turkey. Most of them have wastewater treatment plants, own wastewater treatment plants, but nearly 30% of them don't have any wastewater treatment plants. They deliver their wastewater either to municipal sewage or, unfortunately, directly discharged to the receiving environment, although it is illegal. And in this respect, we make lots of stakeholder meetings, like organized industrial zones, industries, municipal wastewater treatment plants, and take feedback from them. And this feedback that we obtain from these meetings are shown here. Some of the sectors, like textile or plastic packaging, have very water-intensive processes and need feasible water recovery actions. In the majority of the firms, the major water consumption area is the green area irrigation. And they, some of them have plans to use the only recovered wastewater in their processes, but most of them can't achieve this. They have lack of technology, lack of budget, such problems. Some firms cannot achieve the required discharge limits. For example, dairy firms create inlet COD problems, and 83% of water used in the OIBs comes from there. And in some organized industrial zones, pollutants in the wastewater released from the companies to the streams are not treated well. And due to this, it passes through the irrigation, agricultural plants, animals, and finally groundwater, unfortunately. In this respect, these nanobubbles will provide not only more effective treatment of water and can provide water to be recycled, but also protect natural water resources, because these basins here, as you can see, has mostly low class in terms of water quality. These classes and basin prioritization determined by the Ministry of Environment and Urbanization and Climate Change in Turkey. The list order shows the Akarçay, Mainstreaming and Gediz basins are prioritized in the manner of pollution. When we look at them deeper, in Akarçay Basin, water resources are under significant pressure from urban and industrial discharges. Advanced treatment and effective biological treatment procedures must be implemented, therefore, and most of the parameters, water parameters, exceed the limits. This is a problem in this basin. In the Mainstreaming Basin, pressure by industrial wastewater and untreated or insufficiently treated urban wastewater discharge is a problem. Significant portion of the COD load is coming from the industry, and some parts of the basin, mostly pollutant points, for example, Çolbu stream, Ergene is a very big problem in Turkey about this. And in the Gediz Basin, Gediz River and Mist stream are the most distressed streams. There is pollution in most rivers throughout the basin in terms of COD, BOD, like parameters. And 50% of the point COD load volume results from the urban, and 49% from industrial wastewater discharge. So if you want to protect natural resources and provide water recycling in order to conserve the water natural water resources, we need to take some technological renewables. And to come up with the final notes, I want to mention about needs and potential, summarize this. We aim to focus the water sector to transfer this technology to Turkey because organized industrial zones with high water consumption and water scarcity, along with sensitive bases especially, should be focused in terms of the commercialization of this technology. The wastewater originates from industrial organizations, and discharge of this wastewater into the receiving environment without treatment causes excessive pollution on the soil and vegetation due to the water pollution created. Heavy water consuming and highly pollution loaded organizations lack the capacity to treat the wastewater generated sufficiently in terms of both quality and quantity, as I mentioned. It has been seen that in almost 50% of these sensitive bases, the pollution load problem occurs due to the discharge from organized industrial zones into the receiving bodies. And this ratio is expected to increase because organized industrial zones are not operating at full capacity by now, mostly organized industrial zones in Turkey, but they have very high potential. Therefore, the increase in water consumption is expected. And in final, water treatment and recovery needs in organized industrial zones, in these sensitive regions especially, they need attention in terms of nanobubble technology application and commercialization. That's all from my side. Thank you for listening to me. If you have any questions, and then later for our participants, you can reach the Climate Research Association.
Just have the questions later? Or
No, you can ask. You can ask for now, but since this meeting close to any other listeners, I can say, but you can ask also.
I was curious if there are any companies, nanobubble companies in Turkey already working in the field.
No, as we research, there is no company having nanobubble technology.
Okay. Okay. It seems like there's a lot of potential.
Yes, there's a huge potential in this manner.
Are there any questions to Ece? So if there's no questions, our next speech will be by Dr. Onur Opul. Thank you, Ece, and I can give the floor to Dr. Opul. Okay. All right. Are you able to see my whole screen as a slide? Yes, we can. Okay. Well, thank you. Thank you again for organizing this. This is a very exciting project. I'm going to present a lab study about nanobubble aeration for wastewater treatment. This study is led by Sudhira. He's a postdoc in my research group. My name is Onur Opul. Our group is at University of Maine, but as you mentioned, our collaborators in Arizona State University, and the study was also first instigated by NASA Johnson Space Center. This work is on effect of air nanobubbles on activated sludge. I'm going to give some details about oxygen transfer, some oxygen uptake, diversity of microbial consortium after nanobubbles versus traditional aeration. Most of these slides are prepared by Sudhira, and some of those at the end are prepared by my PhD student, my graduate student, Ashton Collins. So I don't think I need to go through the definition. Obviously, nanobubbles present an opportunity because of their small size and their lack of buoyancy. We didn't really believe they existed until very recently. Nanobubbles were a matter of debate because very small, their internal pressures would be very high, and they may implode or dissolve with this pressure. But in fact, we use some modern technologies to determine they actually exist, and their lack of buoyancy makes them not only exist but stay stable in a solution, in a suspension for months, weeks. So I think the best description is these videos. Right. This one is taken by our collaborators at Arizona State University. This is a nanobubble. This is your scale bar of 1,000 nanometers. You can see just a roughly around 100 nanometer bubble. With the flow direction, the bubble is moving. So you can see the contrast, the background. This is taken by a nanotrack analyzer. This is from literature, the next video. It gives a more stark description of the stability and in their independent Brownian-like motion. They are not impacted by each other. They are stable. They are just moving, vibrating a little bit. But as you can see, this technology can overcome the thermodynamic limitations of gas solubility. So if you can pack lots of bubbles in separate domains in water, then you are actually overcoming the solubility limitation at given temperatures. So this gives an immense potential of application. Again, no need to explain this, but typical aeration procedures suffer from large bubbles quickly rising to the surface from diffusers, and then on the surface they pop and disappear.
So basically you have a pocket of gas, and you use this gas as a means to transfer the interface, as a means to transfer gas into liquid. But since the bubbles are large, their retention time is really small. So in a few seconds, they leave the reactors, and that interface is limited to the surface area of this bubble. The large bubbles mean small surface area, short retention time, and basically you are spending resources, money, air, to aerate air. Also, there may be a potential of transferring liquid phase compounds into gas phase in the form of aerosols. So pharmaceuticals, other concerning pollutants may be transferred through the surface of the reactor. The smaller bubbles, we have the idea of microbubbles that has been implemented to decrease their rising speed, slow rising, and increase the mass transfer with increasing surface area, but still they suffer from short lifetimes. The transformative change, again, is no rising nanobubbles, as you saw in the video, basically moving in solution. And the extremely high surface area causes a further improved mass transfer. Again, for a general audience, activated sludge is a biological system where you have aerobic microorganisms and you have your wastewater, and your aerobic microorganisms use oxygen as a terminal electron acceptor and organic pollutants as electron donors with a biological conversion. So basically they use nutrients, oxygen, and food, and improve their size into biomass, and they form carbon dioxide and water. So they mineralize these pollutants into carbon dioxide, and they form biomass. Basically, to capture more food, they typically get more sticky on the exterior with a polymeric substance. So they get more sticky, meaning that they eventually form a large flocculated biomass that settles down. So that's how wastewater treatment works. So of course, as you can see, oxygen is a key component. The more oxygen you provide, the better destruction of organics, the better growth of aerobic microbial microbes. And a typical wastewater treatment plant, this is our local treatment plant. It's a 4.5 meter deep tank. At the bottom, you have diffusers. So these diffusers are membrane type, so they blow up like a balloon as the pressurized air goes through, and they provide oxygen in the form of large bubbles. Approximately 1 to 4% of all American energy production goes to providing air to municipal wastewater. So we are looking at a massive amount of oxygen, and the mass transfer efficiency of this process is around 30%. In the matter of a few seconds, the bubble that leaves the diffuser goes to the surface and pops and disappears, meaning that you have lost 70% of the oxygen that you would like to provide to air. So that's why we think the nanobubble technology presents an opportunity in terms of improving mass transfer and not disrupting the microbial. Of course, microbial activity is not just one type of microorganism, it's a community of microorganisms doing the job together. So with nanobubbles, we don't want to disturb this. And also eventually the biomass, as I said, settles down. The solid sludge, we call it sludge. The sedimentation also should not be disrupted. So we did a bunch of systematic experiments in a bucket with a nanobubble generator. We used nanobubble aeration in situ for this batch reactor. We provided this amount of air with and without nanobubbles and compared if nanobubbles make a difference. So here is another video. So this is nanobubble aeration. As you can see, that creates a vortex with this line. This white line is the gas input. This black one is power input. So you basically create tiny bubbles as this nanobubble generator operates. And then we just take this offline and bypass this and apply the same amount of air in terms of regular bubbles, small enough that both of these reactors are fully mixed, small enough that both of these are fully mixed. So the first results were obtained in distilled deionized water clean system. Nanobubble aeration created about 15% better nanobubble air, oxygen content. This is your oxygen content. Actually in a matter of a few seconds, in fact, our first data point was a minute, you are already more oxygenated, more aerated than your coarse bubble. This is the traditional coarse bubble aeration. And then if you don't aerate this, this is a control. There is no change in oxygen content. So coarse bubbles increase that oxygen, dissolved oxygen slightly, nanobubbles more. If you convert this knowledge into gas transfer efficiency in terms of KLA, you are looking at a 3 times faster gas transfer efficiency with nanobubbles. This is the quantification of nanobubbles, again in DI system. This 3D figure how big the nanobubbles are. They're typically always less than 600, 500 nanometers. How many of them? Have a couple million of them, and per each size. So these are all histograms. If you condense this information to these 2 figures, as you aerate the system, the concentration of bubbles increase, so we don't lose them. So we have about 60 million nanobubbles after 6 hours. And then their size gets smaller and smaller. Probably large ones coagulate and leave the system, but the small ones remain. So as you aerate the system, you get a shrinkage in average size, but increase in concentration. Here is the next set of experiments where we actually this time aerated instead of DI water. We took some sludge from local wastewater treatment plant. Same nanobubble system versus regular aeration. Again, we achieve complete mixing in both systems. And we have to assume, because there is no way that we could measure nanobubbles with a microscope or nanotrack analyzer in sludge because it's such a dirty and complex matrix. We assume that our measurements in DI water are deductive enough for this complex media. This is just an assumption. So here's the first set of results for COD removal. This is a metric for pollution, how much chemical oxygen demand in the system. It's a standardized metric for how dirty the water is. And we typically try to remove COD. So in 2 hours, our COD removals between for regular aeration is 10, nanobubble aeration is 30% almost. In 2 days, this percentages approach to each other because it's a batch system. The amount of pollution is limited, so you basically approach a plateau of 65 to 75%, but still 10% increase in aeration. Solubility efficiency. Once again, just to make sure that we don't disrupt the microorganisms in there, we counted the number of filamentous structures in the sludge, because filamentous bacteria is the backbone, is the spine of a microbial flock. So they just basically attach to it and create these communities so they can settle down easily. If too much oxygen, if filamentous bacteria loses their advantage and they start disappearing, it's hard to maintain a filamentous bacteria. So they just start losing their advantage and they disappear from the system. As you can see, it was actually true. A coarse bubble aeration almost had twice as much as filamentous bacteria in 12 hours, and in 2 days, we lost about 7 per sample. So here's an example. This is what a filamentous bacteria that basically helps form a flock and makes it easier to settle down. And as you can see, the coarse bubble aeration, the nanobubble aeration seems to be settling better, but in fact, this the clean water or the supernatant is actually more turbid. So it basically had a negative impact on the way that filamentous bacteria help clear the water. But in nanobubble aeration, we had less sludge because we basically converted them into carbon dioxide. But in terms of turbidity of the supernatant, we didn't do as good. And here's relative abundance. This is too technical of a microbiology study, but basically the relative abundance of these particular species based on a DNA analysis also indicate that there's a stark difference between nanobubble aeration versus coarse bubble aeration, and some of these bacteria are associated with flug formation. Here's this the 356 genera identification through DNA analysis, and I'm not going to try to go into the details of this, but basically nanobubbles create a different condition, and this flug community it changes drastically, giving some bacteria advantage, and then it changes the structure of the community that requires additional research. This is just another way of representing the same data. Coarse bubbles versus nanobubbles form very diverse and different clusters of microorganisms. So currently we are working on a model that's based on this wastewater treatment plant. We are trying to scale this down, these large diffusers, into, this is Ashton's work. We scaled it down by 1 to 34. We have these fish tanks, 75-gallon fish tanks, and we know how much to fill this up to exactly represent the wastewater treatment plant. All these pipes actually are connected to the same gas source, and that you cannot see it well, but all these pipes actually have the same number of diffusers in the form of little holes. We pump 20 standard liters of air into the system per minute, and we compare nanobubbles in terms of cost and energy consumption. This is our nanobubble generator. We have 3 right now. Only one of them is set up, but Kenneth is working on setting them up. So we are comparing same exact air inputs, but one with nanobubbler, one with regular aeration. My last video. So this is a regular aeration that resembles aeration in a treatment plant with diffusers, and this is nanobubble aeration. Side by side. I think we only have preliminary data and we don't have cost analysis, but our next steps, basically nanobubbles again created a slightly better advantage. If you look at the scales down, we are here around 9, 10 in different locations of the fish tank, top and bottom, and 9 different locations. And nanobubble aerator, we are in the range of 10.5, regardless of the top or bottom, and in both conditions, we know there's better aeration with nanobubbles, and in every location we have a similar distribution, uniform distribution. Average basin is 9.9 versus 10.5. And this is a kinetic change. This data is from yesterday. Dissolved oxygen basically goes up faster with nanobubbles, but we are currently repeating this to get some statistical robustness. Well, just to cut this in time, I'm not going to read all of them, but nanobubbles provide more gas into solution. There's approximately 10% better soluble COD consumption, pollution consumption. We decrease the amount of filamentous bacteria that are good at capturing oxygen, but they basically makes it worse for sludge to settle down. And the flug-forming bacteria changes significantly. And with this, I would like to thank the funding agencies, Maine Space Grant Consortium, Town of Orno, which has helped us with the scaling down of the treatment plant, and also Climate Research Association for financial support. Sudhira is not in the meeting today, but he's right here. He prepared most of these slides. Ashton is doing the cost analysis, cost calculations, and Zach helped collect these dissolved oxygen measurements in the system. So I'll stop sharing and answer your questions now or after the workshop.
I think there are no questions right now. Thank you, Dr. Opul, for your great presentation and your work, for sharing it with us. So I would like to continue with Dr. Sergio Garcia Segura. and with its
I'm trying to activate the
presentation.
camera. I'm
Okay,
trying to
no
activate the
problem.
camera. It's not working. I don't know why.
That's okay, no problem.
I hope it's okay. Let me share screen, and please let me know if you can see the presentation. Can you see the presentation?
Yes, we
Yes.
can see it. Thank you.
Okay, well, thank you, Sena, for the introduction. So it's my pleasure to kind of like participate of this closing workshop from the project. We will be talking today about nanobubble interfacial reactivity and impacts on water chemistry. We are going to be talking specifically about CO2 nanobubbles, which are a kind of gas that has not been that much studied. This is a work that we have been doing in collaboration with the group of Honor too. And I would like to start this presentation kind of like providing a quick research group background on what we do and where we are. So we are located at Arizona State University, which is in Phoenix, Arizona. It's a very hot desert climate. So we have a lot of water scarcity and water issues too. But our university is ranked as one of the top universities in the world and #1 in innovation in the US for the last 6 years in a row. We have cutting edge in infrastructures and facilities, and we do kind of like very cutting edge research. Our group is also part of a research center called NEWT, which is Nano Systems Engineering Research Centers for Nanotechnology-Enabled Water Treatment, funded by NSF, and involves 4 universities. And we have about 30 industrial partners that also fund and are interested in the kind of research that we do. The scientific mission of my group is to develop the next generation of water treatment systems and meet the growing industrial societal needs for off-grid water supply. And we do that kind of like following the need approach, benefit competition approach on thinking what specific needs we are trying to overcome and how our approach can be better than other existing processes. And we explore not only fundamental, but also applied research trying to innovate. The focus of the research on my group is mostly kind of like developing new interfacial processes, which involves electrocatalysis, photocatalysis, and nanobubble technologies. In terms of the environmental and scientific motivation that we have, this is around the topic of water. We are very concerned about water issues, water pollution, and how we can remediate issues. If you think about water, water is the center of all the ecosystems in the planet, is an element that we need for life as we know it. But our activity as humans in our daily life or industrial activities generates different kinds of pollution that dramatically affect the quality of our waters. And not only this, but it also affects all the living beings that depend on them, including ourselves. And this is a challenge that it's not only about us, it's about future. And we have to think how we can transition to more green, sustainable, and efficient methods that enable kind of like this water treatment and its reuse. If we think in terms of the sustainable development challenges defined by the United Nations, clean water and sanitation is one of the main challenges that have been highlighted. And this is simply that tons of people have no access to simple clean drinking water or even sanitation in the world. And if our holistic objective is to reach this goal of having access to clean water and sanitation for all before 2030, we are kind of like delayed. If we are thinking on how we can achieve these goals and how we can ensure access to water, especially in water-stressed communities, as you were all kind of like discussing about the issues in Turkey, which is not only Turkey, it's all the world that's facing the same challenges. We have to envision and redefine our horizon based on new technologies that will be enabling us to reach these goals. Here is where nanobubbles kind of like have a potential impact, and I will not spend a lot of time talking about them because all the workshop is about this. And I think that we have had a nice overview. But these nanobubbles, which are nano entities or nano-sized metastable gas particulates that have very, very small diameters, present unique properties induced by the nanoscale effects. And these nanoscale effects are the things that we are especially interested in, and we are trying to elucidate how they can impact different water treatments. And one of the most interesting aspects of these nanobubbles is that this gas-liquid interface that we form can actually may be modified by the accurate selection of which kind of gas we want to use. When we think about these unique nanoscale properties that nanobubbles have, that can kind of like enact different possible applications in terms of water treatment. And so some of them were covered thoroughly in the first session, so I will not be entering into detail on how we can use nanobubbles for different applications. And I will focus a little bit more on why we are studying CO2. If we think about CO2, it's everywhere, isn't it? It's one of our greenhouses, but it's also part of many metabological processes in the environment. And it's extremely important because CO2 content in water is what provides alkalinity, which is a natural buffer capacity to control pH changes. And CO2 has many applications also nowadays. CO2 is one of these gases that's very, very interesting because I was saying it's part of the carbonate systems in the environment. It's an acid gas that can be dissolved in water. And when it gets dissolved in water, it actually reacts, forming carbonic acid. And this carbonic acid has two different species, hydrogen carbonate and carbonate, that can remain in solution and control what I was saying, drastic changes in pH. So the objective of this study was to understand a little bit more how the CO2 nanobubbles interfacial reactivity, because this is a reactive gas that can be dissolved in water, generating acid-base species, can impact the water chemistry. So what we did is we worked with a system treating 50 liters of water. 50 liters is starting to be something kind of like in terms of a big volume of water. And when we bubble CO2 nanobubbles in there, we can see drastic differences between conventional bubbling and nanobubbling. In this graph here in the right, what you are seeing is the plot of the change of pH over time. And we see that when we bubble nanobubbles, we get to the standard condition of 4.5, which is the solution of this CO2, in less than 1 minute. And this is extremely exciting because we are drastically changing the pH of our water, and CO2 bubbling is one of the things that are used to control pH after kind of like drastic changes of pH in water treatment plants. So what I was mentioning here is that this can actually revolutionize the way that we deliver gas into gas-starving systems, because we can change drastically these physical-chemical parameters of the water. Other aspects that we were being interested about it's not only the fact that we are seeing this drastic or fast change of pH, is what we call the volumetric mass transfer coefficient. What's this volumetric transfer coefficient? So if we think about a two-film model, so we assume an hypothetic stagnant film layers of gas and liquid at the gas-liquid interface, there is obviously a gradient of concentrations from the gas species to the bulk of the liquid, which will result in the dissolution of these species. This is the way that we are kind of like usually in any system that requires gas, like the one that Onur was describing for aerobic treatment. We need to deliver gas into the system. And when we do this, there are 3 sequential steps that are very important. The first is the diffusion across the gas film of thickness delta, which is the part where we are having the concentration from the bulk of the gas to the bulk of the liquid. We have an interfacial equilibrium at the boundary between 2 phases. And then we have another molecular diffusion from the liquid film to the bulk liquid. This is translated into the resistance for the transport of these species, which it presents this equation. And I will not enter in details, but when we are considering the transfer of CO2 into water, which also involves a chemical reaction, these expressions get to look like this, where this KLA, which is our volumetric mass transfer coefficient, it gives us an indication on how fast we can transfer this gas into the liquid phase. When we do these calculations and we try to compare our nanobubble system with our macro bubble system or coarse bubble, the general that we use, we can see that there is a difference of 1 order of magnitude. In fact, just because using nanobubbles, we can get 11-fold higher mass transfer than traditional bubbles. That without talking about the higher efficiency of gas transfer, because nanobubbles have a smaller diameter, they have a huge interfacial area that actually favors this transport. And the question that Onur well mentioned before and that a lot of scientists have been discussing for a long time is, do nanobubbles exist in solution? And the question is, the answer to this question is yes. We have been conducting also fundamental studies evaluating the sizes of these nanobubbles, and you can see how at different times of generation, we can accumulate different sizes of nanobubbles in different quantities and amount. But we are talking about huge amounts of particles that when you integrate these different areas of distribution, usually are about 10 at the 8, which is a huge number of very small interface particles. The other question that we ask ourselves all the time, simply because we're talking about these bubbles that are metastable, and they are present in the solution, how long these nanobubbles last? And this is a very interesting question because it depends on many, many factors. Is this open system to the environment? If it's open, it may reach equilibrium faster. So these nanobubbles may disappear faster than if you have a closed system. But for open system, which is most of the cases scenarios, in the case of these CO2 nanobubbles, we actually conducted a study of the stability of these nanobubbles over time, and we saw that they can last over a week. If you think in terms of a conventional bubble, when you form a bubble, this rapidly and suddenly leaves the solution very quickly. It has a retention time in the liquid of probably 1 second or 2 seconds, tops. But for nanobubbles, that means that our interface of gas remains in solution for 7 days in the case of CO2, which means that we will have much more time and much more efficient contact of the gas with the water, and we will enable this transport that we were talking before. The other aspect that's very important is how these CO2 nanobubbles may affect the water chemistry. As I mentioned, the CO2, it's an acid gas, and it will have acid-base reactions in our system. And one of the things that can be affected is the buffer capacity. A buffer is a chemical or substance that, when it's in solution, can resist the change of pH when we are acid or alkali species. Having a CO2 at this pH 4.5, what we have is something that can resist to the addition of alkali, and we actually evaluated this in this graph that you can see here. These are the units of pH, and here we have normal water that you see that addition of OH drastically changes the pH very, very quickly. These changes when we add CO2 bubbles, these macro bubbles, that what they do is they start inhibiting this drastic change because we have an acid species dissolved that will consume these OHs, preventing this quick transition to an alkaline pH. But if we compare the coarse bubbles with the nanobubbles bubbled in the system for the same exact amount of time and the same exact amount of gas delivered to the liquid, we see a huge drastic increase of this buffer capacity. You can see that here we have addition of a lot of millimoles of OH, and this is barely changing our pH. And if we calculate what's the buffer capacity, we can see that in these conditions, just nanobubbling can increase by 7-fold. 7-fold, it's a lot of increase of the buffer capacity of our system. This is related to the fact that because we are using these nanobubbles, that they remain for longer time in the solution, we have a larger availability or a hidden availability of carbonates coming from this CO2 that was remaining stable within the bubble. The other question that we may have is, do these nanobubbles increment availability of other gases? And the answer is yes. So the work that Honor was presenting before, which you can find the reference here, I will recommend the reading of this interesting article, demonstrates that we can use different gases and increment the performance of any gas-starving system, like, for example, the aerobic treatment. And this has not only impacts on the performance of our system, but it also has impacts on the biovolume of the sludge form. So we can actually reduce the biovolume of our system, which is where high expenses are associated to these biological treatments, how you treat this volume of sludge. So to finish the presentation, that is kind of like short, we had only kind of like 15 minutes. I would like to share kind of like a main take-home message. And this main take-home message is that these nanobubble technologies can actually become a paradigm shift for gas-starving systems. Any gas-starving system that you can imagine, any technology that requires gas or interface of gas in a liquid, nanobubbles can actually increase them very, very much, at least in 1 order of magnitude scale. And that means that the opportunity is just ahead. All this study on opportunities of nanobubbles has actually demonstrated all the potentials that these technologies may have, but still, we have a lot of work to do prior to successful market implementation. There are a lot of efforts from industry demonstrating that these technologies work better than conventional aeration systems, but we need a scientific proof, which is what we are trying to do in collaboration with Honor, to demonstrate why these technologies work better. So thank you very much. I will be happy to answer any question if there is any. And I will share kind of like, as Honor did, the photo of my group. This work was conducted in part by André Magdaleno and Gabriel Cerrón Calle. Both of them are now PhD students in my group. So thank you very much. And Sena, you kind of like, I give you the torch back.
Thank you very much, Dr. Segura. Do you have any questions for Dr. Segura? Or we can take them at the end of the workshop as well. I think there is no question. So in order not to take your time too much, I will be continuing with Mr. Anıl Doğuş from Eskon Energy. He will be giving a presentation on the energy efficiency in wastewater treatment plants.
Hello, everyone.
Hello.
Hello, hi. I'll share my presentation.
Okay, thank you very much.
Can you clearly see?
Yes, we can see your screen.
Okay, thank you. Hello again. My name is Anıl Doğuş from Eskon Energy. I'm the head of energy services department in Eskon, and I'm a mechanical engineer and have been working for more than 10 years in energy efficiency sector. And in my session, I will give a short overview about energy efficiency in wastewater treatment plants. As all of you know, that the main purpose of the wastewater plants are to treat the water, of course. The most of them are not or were not designed or constructed concerning energy efficiency. But due to energy crisis, sustainability concerns, and climate change, energy efficiency is one of the crucial topic in any kind of sector, also in wastewater treatment plants. And there are some figures that show the energy efficiency or energy cost is a significant operational cost in wastewater treatment plants. The first one is that water utilities, and including wastewater utilities, consume around 4% of total worldwide energy consumption, and nearly a quarter of it belongs to wastewater treatment plants. And also another study reveals that energy costs may account up to 40% of the wastewater treatment plant's total operational costs. I will not dwell on this slide very long, but a typical treatment plant consists of preliminary treatment, primary treatment, secondary treatment, and water recycling, excluding upstream and downstream processes. And all these sections have energy consuming equipments, of course. In wastewater plants, there are some KPIs that help us to understand the energy efficiency level or the energy savings potential of the plants. The first one is the energy consumption per meter cube of wastewater, treated wastewater. This value ranges between 0.28 to 0.61. And the second one is the energy consumption per year per person that this water plant supplies water. This range is between 27.4 to 0.9. And the last one is the energy consumption per chemical oxygen demand. As a rule of thumb, as wastewater solid concentration increases, the specific energy consumption decreases. The specific energy consumption increases as the actual load rather than nominal capacity decreases, and the higher nominal capacity means generally the lower specific energy consumption. And also in a conventional typical wastewater treatment plants, there are three main energy consumers. The first one is aeration process, the second one pumping, sludge pumping, and the third one is sludge dewatering processes. On the table, you can see some energy indicators for 10 different countries, and the kilowatt-hour energy consumption per treated wastewater in meter cube. These values ranges between 0.08 to 0.73. In Turkey, one estimation is around 0.35 kilowatt-hour per meter cube, according to some energy audits conducted in certain number of municipalities in Turkey. This value is around the average value of the expected values that I showed in previous slide. Regardless of the sector or the facility, energy efficiency is a holistic approach indeed. And in wastewater plants, there are some key elements that affect the energy efficiency level or energy savings potentials in the plant. These are resource plant supply nexus, degree of solid concentration in the wastewater, wastewater amount and characteristics, hydraulic condition of the plant, treatment process technology, plant equipment technology, plant age, chemical resource requirement, and energy supply, energy sources. In facility-based energy approach consists of four key elements. The first one is operational efficiency. The second one, equipment technology. Third one, behavioral impacts. And the last one is predictive maintenance. While assessing energy efficiency, we focus on three areas. The first one is energy efficient equipment or systems. The second one is energy generation, biogas or gasification. The third one is renewable energy generation, either with solar energy or hydroelectricity. Of course, independent studies should be carried out on each subject while preparing or assessing the energy efficiency roadmap of the wastewater plant. In terms of equipments, as I said earlier, the main energy consumers are pumping systems, aeration unit, and sludge treatment unit. In these units, we need to assess the pump efficiencies, blower efficiencies, air compressor efficiencies or waste heat recovery potential, aeration automation, bubbling aeration efficiency, lighting efficiency, electric motor efficiency, transformers, if it's possible, treatment at source, mixer efficiency, free flow water circuit, and recovery of backwash waters. In pumping, aeration, and sludge treatment processes, there are some typical projects that can be implemented. And these are installing variable speed drivers on pump systems, replacing motors and pumps with high efficient models, and using automation systems to optimize the operational parameters. And in aeration unit, replacing inefficient blowers with energy efficient ones and installing variable speed drivers. And in sludge treatment unit, improvement of the dissolved air flotation thickening process and replacing centrifuge equipments with screw press or gravity belts. In the context of this workshop, the nanobubbles also have significant effects on energy efficiency in the plant, thanks to their two advantages. The first one is that they can diffuse and disperse in the wastewater volume more efficient way, and thus increase the aeration efficiency. And the second one is that nanobubbles can remain in longer time and thus decreases the blower air loads. In renewable energy technologies, we can analyze the biogas cogeneration systems. We can produce facility electricity. We can use the waste heat to heat up the spaces. And also we can use that waste heat to dry the sludge. And also in photovoltaic systems, on-site production can help reduce the plant's electricity demand. And also heat pump options can be assessed, and wastewater can be used as a heat source for water-sourced heat pump systems in order to produce hot water. And this hot water can also be used in space heating or any drying processes. Of course, there are lots of projects. What in order to evaluate the projects, we should use a prioritization matrix to decide which projects will be implemented first. In order to do that, we developed a simple matrix that consists of 4 key parameters. The first one is project effect on system scale, savings at system scale. For example, a variable speed driver can increase pump or motor or blower's efficiency, for example, 40%, but may not have substantial effect on plant energy costs, but it does affect on equipment. The second one is savings at plant scale. For example, biogas or photovoltaic systems have substantial effect on plant energy consumption. The third one is technical viability. Again, for example, variable speed driver is an easy project to install, but a photovoltaic system is more complicated. And the last one is return on investment, of course. The less, the better in this topic. So we should analyze the projects in terms of these parameters and score them from lowest to the highest, and we can decide which project will be the first. Of course, facilities should develop and expand this matrix according to their own priorities. That's all from me. Thank you very much.
Thank you very much, Mr. Doğuş, for your presentation and
You're
informing
welcome.
us about the
Thank
energy consumption in wastewater treatment plant. Is there any questions from the participants for Mr. Doğuş? I think not. So we can continue with our last presenter, Mr. Seth Connell from Wastewater Technology. He will be giving a speech on nanobubble generation technologies. So I can give you the floor, Mr. Connell.
Okay, thank you. Let me go ahead and try and share my screen. Let's see. Okay, so can everybody see my screen?
Yes, I can. Yeah.
Okay.
Is anyone? Yeah.
Okay. So my name is Seth Connell. I'm the CTO at Nanbubble Technology over here in Seattle, Washington, on the opposite end of the country as Lenore over in Maine and Sergey over in Arizona. So what we focus on is nanobubble generation and engineering water to advance industry towards a cleaner future. Quick little bit about our company. It's we're a small startup led by our CEO Kurt Kung, who's a Taiwanese national, and he went to University of Washington, dual PhD in nanotechnology and electrical engineering. I have extensive experience in engineering and CEA and indoor agriculture and agriculture technology, as well as been involved in a variety of climate tech partnerships and founders groups and stuff like that. And then our advisor, Michael Holt, he has extensive business experience in not just the startup scene, but also in academia. He's worked with Kurt on multiple NSF projects in the past. And we've all worked together on various levels before getting together to start Nanu. So, but nanobubble characteristics, this has already been touched on a couple of different points, but these are, bubbles that do exist in nature in very small quantities. But once we're able to utilize them and generate them up to higher quantities and concentrations over 100 million per milliliter is when we really start to see measurable effects on different aspects of water use. And as discussed, there's the size and density. They're very small, smaller than 500 nanometers. They have a high internal pressure, and when those bubbles burst, they release high heat and also produce sanitizing hydroxyl radicals. The surface charge of these nanobubbles enables them to essentially bind to charged mineral ions of the opposing charge, and depending on what the constituents or electrolytes are in the water solution that the nanobubbles are being generated from, can determine whether or not these bubbles are positive or negatively charged on their surface. And then there's the non-buoyant factor, which allows them to stay in solution for weeks to months at a time. So for the different variations of nanobubble production, hydrodynamic cavitation utilizing the Venturi effect is one of the more common ones. And this is one that we've been working with a lot, where essentially you have water flowing through a tube or a pipe, and that it enters a constricting area where the velocity increases, but the pressure decreases, which creates a vacuum. And there's inlets where gas or surrounding air for direct air capture can enter that tube or pipe and then mix with the water to create nanobubbles through that cavitation effect. And on the right-hand side, you'll see there is a chart from Nanosite, basically showing the typical distribution and size of nanobubbles produced from this method. Very similar to the chart that Sergey showed with those 4 different varieties. Electrolysis is another method that's used mostly in academia. I haven't seen many commercialized products from any companies yet, but this method essentially uses electrodes coated with 15 to 30 nanometer layers of a variety of different substances. Some use polymer electrolytes, membranes, aluminum, palladium, platinum, or graphene oxide. And whenever a direct current is passed through these electrodes, it arcs over the membrane pores and the contents vaporize to produce nanobubbles, and when you increase the voltage, it increases the concentration. And this distribution can be very different depending on the type of electrolyte that is used in the solution that the electrodes are in. Ultrasound or acoustic cavitation is another method. And this one essentially can both create and destroy nanobubbles. So there's a kind of a fine line there, and there's a wide range of frequencies that are used to do either or. And that's one of the things that Onor's team is exploring as well. And in medical settings, this has a particularly profound effect in localized treatment of, say, medicine is delivered via nanobubbles into the body, and then they can basically use an ultrasound device to cause those bubbles to burst in a zone where there's a wound, or there's been surgery, or there's a tumor per se, and it can deliver those medicines in a highly concentrated way to a very specific area of the body. Periodic pressure change is another method where essentially, if you have a syringe, is a common analogy, with water and some air in there, and you put a cap on the end, and you pull the plunger back to increase the volume inside. Basically, it's going to change that pressure, and then once you push it back in, it's going to compress that pressure. And as you do that over and over and over, you're changing the boundary condition where that water meets the air, and you're able to generate nanobubbles with that method. And then the hammer mill, or the water hammer, which I believe is the device that Onur was using in those photos he showed on his slides. Essentially, this method forces water and gas into nanobubbles with a wide variety of hammers, very small hammers on the central axis that rotate at about 3,000 RPMs to produce nanobubbles in highly measurable concentrations. And I have not been able to find or source a actual nanosite profile chart, which is why it's missing from this slide. So within the nanobubble market and competitors and trends, there's about 45 companies around the world since about 2015. Moliere is the most well-known one, and there's also Akiniti, which is the second most well-known. They're from Japan, and then there's a handful of others, including ourselves, that are focusing on expanding the technology. And within that realm, most of the trends in this nanobubble market show companies really focusing on agriculture and wastewater applications. So, just trying to really increase the throughput of the capabilities and get those flow rates higher and higher so that they can be integrated into municipal wastewater treatment facilities, as well as large aquaculture and agriculture operations involving soil, going beyond just indoor agriculture. There's not many companies that are scaling down their technology for, say, like lab settings, or there's not really many other companies exploring SDG contributions towards the adjusting climate impact or exploring new market opportunities. And here at NANU, within our agriculture program, we're working with Gold Standard and Vera, Gold Standard in the EU and abroad, and then Vera here in the US, to essentially create carbon credit programs for our farmers that we work with, so that they can have a passive revenue stream as the nanobubbles treatment using our direct air capture devices. The nanobubble capture is not, it's a very negligible volume, but the impact that it has on the plant growth, upwards from 10 to 30% of increased yields, in turn increases the carbon capture in the soil, which can then be converted into carbon credits through verification processes. And so we're still working on developing those two programs with those verification bodies and certification bodies. And we estimate that at scale, we'll be able to, say at a global scale, if every farm and even forestry was using nanobubbles, that we could sequester 1 gigaton of CO2 per year with an average crop yield increase of 10%. And I'll open it up for any questions, and take it from there. Thank you, Sina. I'll end this.
Thank you very much.
Mm-hmm.
That was very informative, especially in terms of sustainable development goals. It also would, I'm sure, capture the attention of some of the companies or implemented stakeholders. Thank you very much again, Mr. Kanal.
Mm-hmm.
So, is there any questions from the audience? Maybe we can take some questions or take some final thoughts about the project, the Nanobubble technology, its commercialization, especially in this case for Turkey. So I would like to give the floor to everybody from the audience. Yeah.
Maybe this is for you, Sena. Is there governmental support for nanobubble technologies, or I mean, I'm sure there is for energy efficient water treatment, wastewater treatment, but specifically for nanobubbles, are there any programs, or do you? What's your general sentiment?
In terms of nanobubbles, I'm not sure directly is there any support for nanobubbles, but for example, for organized industrial zones, especially for making them more greener and more sustainable, more efficient, there are some governmental supports, and we are also working on those projects with some couple of organized industrial zones as well. This funding might be a good opportunity for commercializing the nanobubble technology via governmental support. It was also a World Bank support as well. I'm sorry, it is supported by World Bank via our government. So this is my view. And Mr. Emre Halkes, do you have any additions to that? You are much expert in that topic.
Okay. Hi guys. There can be a noise, so from the background. Sorry for that. I have my kids right now here. So actually, Sena mentioned the most prominent one. There's this big World Bank funding right now for Turkey's industrial transformation. So industrial zone management, I mean, more than 100 industrial zones in Turkey are after these kinds of advanced technologies right now. Water treatment, wastewater reclamation, wastewater reuse, those kinds of technologies. I think Sena mentioned it rightly. Another area might be some development agencies' activities in Turkey. There are 26 regional development agencies in Turkey, and they are trying to make their industries and their, I mean, more from a broader perspective, they want their areas, they want these 26 regions in Turkey to be more competitive and more environmentally friendly. So they have their own funding sources for regional development. Those kinds of funding sources can be also channeled to these kinds of advanced technologies. These are the major maybe funding opportunities in Turkey. Maybe one more, the National Scientific Foundation. I don't know it in English, sorry, but this major science foundation in Turkey, science funding agency, of course has some funding opportunities for developing these kinds of technologies in Turkey. So Turkey is very mature in, I mean, Turkey is very immature in these technologies. So if there are possibilities to develop these kinds of technologies in Turkey with Turkish partners, there might be some good areas for pilot and demonstration kinds of activities in Turkey's partners. These can be industries, municipalities. So if you can find right partner, you can co-develop these kinds of technologies and demonstrate maybe in Turkey.
Thank you, Sena. Thank you, Emre. I think the overarching goal of U.S. Embassy in Turkey was to promote American industry, American companies to advance Turkish industry by finding cooperation, collaboration opportunities, and with a forward-looking fashion to see if the technologies that are more mature in the U.S. that are field proven, can they advance the industrial scene in Turkey? So I think this platform, for example, Seth and his company Nano Water as a great example, and this is a first step to create this long-lasting, long-term collaborations between Turkish counterparts. Just wanted to spell it out clearly.
Is there anyone who would like to contribute with some thoughts or any questions? I think not. I think our program is over. We have completed all our presentations. I would like to thank everyone for contributing. But before we leave the session, can we open our cameras if possible and have a little screenshot so we can use it maybe in our social media accounts?
And where can we find?
I'm trying to activate the camera, but it's not working.
That's okay. That's perfect. Thank you.
Unfortunately, I was on a business trip, then I just pulled over my car, and I'm in a car.
Thank you, Mr. Rose. So I'm taking a picture. Thank you, everyone.
Thank you, Sena. Where can we find this
you.
recording? And can you spread the slides? Maybe we can create a repository of slides.
Yeah.
If it's okay, if every presenter can maybe send it to you. Is that okay?
Yeah, that would be great. So we can share with other contributors. And I believe we will be sharing this meeting, this workshop in our social media accounts and LinkedIn accounts as well. So we will be surely adding you to those posts as well and let you know. I would like to thank you all once again for your contributions and taking your time and separating your time for our project and this workshop. Thank you all. I hope we can again meet for other projects in the future and have a chance to work together.
Thank you very much, Ruth.
Thank you.
Thank you, everyone. Have a nice day.
Bye.
Bye-bye.